Hello.
Good
So,
morning.
good morning. Okay, so today we are going to complete this topic, the topic of uh, adaptive Ranjakata method. Okay, so just to recall what we uh, talked about this topic last time was that in the adaptive Ranjakata method, we are considering to change the interval of the uh, Ranjakata method, okay, depending on the situation. So for example, that situation can be in the form of this type of function in which the function suddenly changes some value between different points, okay, uh, between some points. So that function change some values. So for this purpose, we need to identify the error in the values. Okay, so there are two methods for the error in the function for finding the error in the function values. One of them is the adaptive Ranjakata or step halving method. So in this case, we find the uh, we take each step twice. So once as a full step and independently, and two half steps. So the difference in the two steps results an estimate of the local truncation error. And that truncation error is divided by 15 and added to the second estimate with the two step sizes to find the refined estimate of the y2. In the other approach, which is called as the Ranjakata-Fellberg method, we use a modified fifth order Ranjakata method uh, to find the fourth as well as fifth order values. Okay, so the difference between the fourth and the fifth order values is the uh, uh, estimate of the error. So for Ranjikata-Fehlberg method, I also shared with you the Matlab program to find the values of the coefficients needed in this method, A1 to A6. Okay. So now since we have found out the error, so we can use these errors, which we can find either by the adaptive Rangekata method or by the Rangekata Fellberg method uh, to modify the step size. So for modification of the step size, we have this formula: h new is equal to h present times the uh, ratio of the delta new to delta present, that is the absolute value power alpha. So this formula is proposed for modifying the step size. So this formula works in a for works for this concept that the step size would be increased if we want to uh, if our current error is less than the error which we want to have in the function. So that means if our delta new is if our delta present is less than delta new, so the value of h will decrease. Or on the other hand, uh, we will decrease the error of the presentation, increase the error of the presentation. Sorry, if we will increase the step size. If on the other hand, when the delta new is greater than the delta present. So in this case, as we can see over here, that it can be used to adjust the step size. In general, the strategy is to increase the step size if the error is too small, okay, and decrease it if the error is too large, okay. That means we compare delta present with delta new. So if this uh, delta present is less than delta new, we will increase the h present, okay. So and like that. So in this case, uh, h present is represent the modified step size. Delta new is our target value of the uh, uh, error, and delta present is our current error, which we can find from either this previous two methods, okay, Runge-Kutta-Felberg method or adaptive Runge-Kutta methods. So in this way, then we find the step size control. So the value of alpha depends on either delta present is bigger or delta new is bigger. So uh, if we have delta present which is less than or equal to delta new, that means our current error is less than the error which is desired, or current error which is less than the desired error. That means the present error is less than the delta new. Then we will use the value of alpha which is equal to which is equal to 0.2. Otherwise, if delta present is greater than delta new, then the value of h will be used as 0.25. So these values have been proposed by Press et al. 2007 in the book by this author. So they have suggested. So these values are most likely some empirical values. Uh, so the effect of using these values is that in those situations when the function will be changing smoothly, so we will be able to increase the value of the step size. Or in those areas where we can find from the error comparison that the value of the function is increasing or decreasing rapidly, we will be able to decrease the value of the step size. So in this formula will work in for that way. So uh, we can calculate the delta present by the previous two methods. The delta new we need to set by some values. So delta new can be found by most in many situations can be found by this formula. Delta new is equal to epsilon times the y scale value. So where y scale value is generally taken as the calculated value of y, and epsilon is an overall tolerance level. Okay, so this type of calculations can be adopted with the help of the some computer algorithm. That computer algorithm has been presented as pseudocode in this in the book chapter over here. So this is the pseudocode for the cache carp RK method. That is the uh, uh, Runge-Kutta-Felberg method. So this is the pseudocode for this one. In fact, I have provided you the Matlab. I have provided you the Matlab program for that. So you can use that as well. And this in figure 25.22, we can use it. We can use it for the uh, is the pseudocode, which is a driver program and a adaptive step routine to solve a single ordinary differential equation. So that means when we want to change the step size, we can use these programs. Okay, so let's see it with the help of the example. Okay. Suppose if you have a equation, uh, this adaptive Ranjagata method is well suited for the following ordinary differential equation. So this differential equation is dy over dx plus 0.6y is equal to 10 and then exponent minus x minus 2 square over 2 over 0.075 square. So if we have this equation, and for this equation, we know that if we don't have this term over here, that means on the right hand side, though, this term is 0 actually. So its general solution will be like this. However, if we want to find its numerical solution and if we plot it, then the solution will be obtained like this. So in the derivative form, if, this dy over dx, this equation will be in this form. Okay, it will be in the form of this bell-shaped curve at a value of nearly 2. That means if we for all values of x, it will be something like a very small value. Okay, dy over dx, this curve value, that means it will be nearly 0. But some values of x near x is equal to 2, this curve will suddenly increase. So this can be represented as a sudden force application during a very short period of time. It is kind of like an impulsive force. So the solution of this differential equation is in this form. Okay, so we can obtain this solution by any of the Ranjagata methods. However, we can realize that we we can change the interval of the step size. Okay, so if we just apply the classic Ranjagata method, as for example in this method. So for example, here I have applied it over here. So I took this equation dy over dx. Can you see this Excel file?
Yes.
Yeah. So if I take this equation dy over dx plus this equation, and I apply the classic fourth order Ranjagata method with coefficients k1, k2, k3, and k4. And if I find the values of this function at an intervals of 0.1. Okay, so then I get these values. Okay, then I get these values. So you can see that the values start from x is equal to 0 and y is equal to 0.5, and then the values start decreasing gradually. And here you can see that from 0.5 the values would decrease near x is equal to 2 to about 0.177, and then between 1.78 and 2 the values are increasing 0.17 to 0.32, and then suddenly there is a jump to 1.05, and then after 2 there is a jump to 1.73 and then 1.79, and then start decreasing again. So if we plot these values, so we get this type of plot. Okay, if we get this kind of plot. So you can see that Uh, Here in this plot, you can see that for the values between 0 to about almost 1.8, this function is decreasing gradually. It's decreasing gradually. But between 1.8 and then to something like more than 2.1 or 2.2, the function suddenly jumps to a very high value, and then it starts decreasing again gradually. So in this case, what you can see that for a gradually decreasing areas of the function, we have a lot of points. Okay, we have a lot of points, but a for this middle portion, we have only a few points over here. So it will mean that uh, the area before the jump and the area of this function after the jump has been very well represented, but the area within the jump has not been very well represented. That means if we want to find a value somewhere here, over here, where I am pointing it over here, I have no known value. I have no known value over here. So this will mean that we need to then we need to now we need to improve or decrease the step size uh, in this jump area. Okay, in this jump area, we need, although here in this where in this gradually decreasing areas, we don't need so many step points. So here we can increase the step size, but in this jump area of this function, we can decrease the step size. However, this we cannot do in this uh, classic Ranjkata methods, because we use a constant value of h. We use a constant value of h, and then we don't have any other way to change this value of h over here. So we can decrease from h is equal to 0.1 to h is equal to 0.05. So here all the values of the h have been decreased, and then if we plot it, so we get a similar plot as before. Okay, we get a similar plot as before. So you can see that these values are decreasing gradually, and but where the value is jumping very rapidly, we have very few points over here. So in order to solve this problem, where in the area of the jump we need more uh, points, or we need a smaller step size, we need to do an adaptive Ranjkata method. Okay, so for doing this adaptive Ranjkata method, so we have two approaches. So these two approaches we considered. Okay, so one was this Ranjkata, this adaptive fourth order Ranjkata method, where we find the difference between the full interval and the half interval, or in the Ranjkata Fellberg method, where we find the difference between the fourth order and the fifth order estimate. So this error estimate is found from these methods, and then we apply the step size control, and we use the computer algorithm to adaptively change the interval of the points. So by adaptively changing the interval of the points, you can see that the first interval is something like, if it is 0, this is 1. So first interval is something like 0.5. But here at this point, we have determined that the function is decreasing gradually. So by the adaptive Ranjkata method, so it automatically increase the interval. So here we don't need so many points to determine. We cannot lose much accuracy by having a smaller intervals over here. We cannot lose much accuracy by having a larger interval over here. So therefore, we have the interval size has been decreased. But by reaching over here, the algorithm will find out that now it is very nearly, we will be changing this function will be changing very rapidly. So therefore, the function automatically, therefore the algorithm decreases the step size. And then here you can see that in this area we have many small intervals over here, and then which will show that many small so many different points which have been determined. So it helps to more accurately determine this part of the function, by having, by decreasing the step size, and by inserting the more number of points in this part. So where it is rapidly changing. And then again, the function determines that when after reaching over here, the function determines that after that point, the algorithm determines that the function is decreasing gradually. So the algorithm will increase the step size. So therefore, we don't need to determine so many different points. So this type of approach can be included into the computer algorithm, and therefore we can efficiently find the therefore we can efficiently determine um, we can efficiently determine the numerical solution of the given differential equation. So that means we don't have to do unnecessary calculations. So the computational time in the computer can be saved. Okay, so this is what it has been done in this example. We will not adopt this algorithm. We can, I can illustrate it to you on Matlab. So for example, on Matlab, if I have this, so for example, maybe, okay, just clear everything and clear screen. So on Matlab, if I have okay, sorry. On Matlab, if I have this equation, okay. So first of all, I can write this equation in Matlab, okay. So this equation, okay. So this in Matlab, when we write this equation will be written as dy over dx minus 0.6 plus 10 and then exponent of this function. So if I want to write this equation into the Matlab, so what I will do is I will write it as, for example, this is example. I will write it as in the M file. So it will be a function. Okay. So I can write it as dy dx. Okay, and this is the name of the variable. I will give it to the function name. And I can, so this is the name of the function dy dx, and then this function is in terms of x and y. Okay, and then I will equate it to yp. Okay, that is the predicted value of y. And here in the second line, I can define the function. So yp will be equal to uh, yp will be equal to minus 0.6 times y. Okay, here you have dy over dx is equal to 0.6y we will take on the other side, so it will be minus 0.6y, and then it will be plus 10 times exponent minus 0, so it will be 10 times exponent minus, so if you see that it is what, 10 times exponent minus x minus 2 square, okay, x minus 2 square, so it will be x minus 2 square, where is it, exponent. It will be x minus 2 bracket close square, okay, and divided by 2 times 0.075 square, and then bracket close, and then bracket close. So it will be like that. And then I will end it. Okay. So in this way, I will write it like this. So you see this function again over here, 10 times exponent minus x minus 2 square divided by 2 into 0.0575 square, and then like that. So I have this value. So I have saved this function over here. So I will save it. So I will save it as dy dx. Okay. Okay. So I saved it with this number with one. Now I can recall the ODE. Okay. So I can recall it as ODE 45. You can, this is the solver for the ordinary differential equation. So I will recall the function as at dy dx, okay, and then comma, space, and then this function have to be integrated from 0 to 4, 0 to 4, and its value was 0.5 for the initial value, and then I will close the bracket. Okay, so here we can see that I will it was yeah. So from x is equal to 0 to x is equal to 4, and its initial value is 0.5. So y0 is 0.5. Okay. So this we have applied it over here, and then I will hit enter. Okay. So after putting the semicolon, I will hit enter, and then I will see the result. So in this case, I am getting this value over here. So you can see that. So can you see this curve on the screen?
Yes.
Yeah. So here you see that one thing which you can note is that I did not put ODE 45 equal to some variable. Normally you can take two variable and then you can find the values of t and y, and then you can plot these values. But I put it without that, and then in fact I got the direct result. So here you can see that the intervals have, there are some constant intervals over here. So in this case, the intervals are not being increased, but constant intervals, but at a relatively bigger intervals. But as soon as we reach near this abrupt change area, the intervals gradually decrease. Okay, intervals gradually decrease so that we can have more accurate values in this inner portion over here. And then again, you can see that when we go past this abrupt change area, the intervals have decreased over here. So in this case, the inbuilt function inbuilt function which we use in the ODE 45 use this kind of functionality already. So they are already adaptive. They are already using the adaptive Ranjkatha methods. So this is what I wanted to illustrate by this. Okay. On the other hand, if you can, if we just want these values, for example, x comma y, if we means if we equate them to x, sorry, x comma y equal to this. So we will get the x and y values over here. So in this case, you can see that x has a 57 by 1 and y is a 57 by 1 interval. And then we can plot x versus y, x versus y. So we will get the same answer. So let me remove this. Plot xy. So, and we can plot it by some circles. Okay, so we can put O, K. O is for circles, that means circular markers, and K is for the black color, or we can use even red color as well. Okay, so I can put OR. So here you can see that I will get this plot in the form of the circular markers, and these markers are having a larger step size, and then near this abrupt change area, the step size decreases, and then we have the bigger step size. So in this way, we can do it like this. So if we don't put x, y, then you can directly get this plot. If we put the x, y over here, so we can get the values of x and y, and then we can plot them by these commands in the Matlab. Okay, so so this was the last topic in this chapter, Ranjkatha methods. So with this, I have covered all the topics of this course, and therefore I can say that we have completed the course of this course. Okay, so then